Welcome to this comprehensive technical overview of ship power management systems and their operation. Modern vessels rely on complex electrical grids to ensure safe and efficient operation. In this tutorial, we will explore the flow of power from generation to consumption, and the critical differences between high voltage and low voltage systems. At the heart of the ship are the generators. These massive engines convert mechanical energy into alternating current electrical power. Most merchant ships use 3 or more generators to provide redundancy and handle varying load requirements. The primary electrical output from these massive generators is directed straight to the vessel's main switchboard. This is the central brain of the power system, where power is synchronized and distributed. High voltage systems, typically 6.6 kilovolts or 11 kilovolts, are common on large vessels like cruise ships or container carriers. The primary advantage of high voltage is the reduction in current for the same power output. This allows for smaller cable diameters and lighter equipment, saving significant space and weight. However, most shipboard consumers, like lighting and domestic appliances, require low voltage, usually 440 or 220 volts. To bridge this gap, we use step-down transformers, which are static devices that reduce the high voltage to safer, usable levels for distribution. These static devices reduce the high voltage to safer, usable levels for distribution. The power flow follows a precise path from the generator to the main switchboard, then through bus bars and circuit breakers to the transformers. From the transformers, it flows to distribution boards, and finally to the end, consumers like motors, pumps, and accommodation systems. The sophisticated power management system, or PMS, continuously monitors and regulates this power flow. It automatically starts or stops generators based on demand, ensuring there is always enough power while preventing blackouts. Safety is paramount. Circuit breakers and protection relays are installed at every stage to isolate faults, and understanding this flow is essential. Deeply understanding this intricate power flow is absolutely essential for every marine engineer on board. By managing load and voltage efficiently, we ensure the vessel remains operational in the most demanding conditions at sea. Now let's take a much closer and more detailed look at the interface of the generator control unit. Successfully synchronizing 2 generators requires perfectly matching their output voltage, frequency, and phase angle. Once synchronized, the breaker closes, and the generators share the load proportionally. On the actual distribution side of the system, we have both primary and secondary distribution levels. Emergency generators provide a fail-safe, powering essential services if the main power fails. These critical essential services include emergency lighting, navigation equipment, and the main steering gear. Bus tie breakers allow the main switchboard to be split into 2 independent sections for maintenance or safety. Shore power connections allow the ship to shut down its engines while in port, reducing emissions. Power cables on ships are specially designed to be flame retardant and low smoke. Regular maintenance of the PMS involves testing protection relays and cleaning switchgear. Modern ships are moving toward integrated full electric propulsion, which allows for even greater flexibility and fuel efficiency by optimizing engine usage. The evolution of ship power systems continues to prioritize sustainability and reliability. From the hum of the engines to the light in the cabins, the power flow is the lifeblood of the ship. Mastering these systems ensures safety for the vessel, the cargo, and most importantly, the crew. We hope this guide has provided a clear understanding of maritime power management. Thank you for joining us for this in-depth technical session on maritime power systems.